Okay, we'll begin. Are there questions?
So,
Yes, go ahead, please.
sir, after inflation, during the process of reheating, like, do we have homogeneity in the sense that we have today?
Yeah, we do have homogeneity because inflation makes everything homogeneous, right?
Yeah. So at the start of equilibrium, yes. Now, suppose we were to ignore inflation for a while, like let's say the universe didn't have inflation,
Okay.
and like for now also forget about the horizon problem.
Yeah.
And so like just by our observation, what should be the scale of homogeneity at this t equal this recombination time,
It will be
during which
60 times the horizon scale at that time. Because at least 60 times, right? Because you see the microwave background is uniform, right? That means over the scale of diametrically opposite points on the large scattering surface, the universe was homogeneous,
yeah,
right? And that's about 60 times the horizon size if we ignore inflation.
horizon at that time.
Horizon at that time.
Yeah, I want, like, today we like said observational number of like some 100 megaparsecs. I'm not sure what the number is.
250 megaparsec. Yeah.
Yeah,
Okay.
so 250. So what would that number be like over which?
This number is the lower bound, right? That it's because this inhomogeneity arose because of the gravitational pull. The small, this 1 in 10 to the 5 inhomogeneity that was there in the CMB sky at the time of
Yeah.
last scattering, right? That has grown into big inhomogeneities, right? And that's the reason why we see inhomogeneities at small scale. But one can show that over the large scales, the inhomogeneities grow slower. Okay, in fact, this growth we will study later maybe. But you can do a perturbation analysis, and one can show that the large scale inhomogeneities grow at a slower speed, right? And that's why we still see homogeneity over large scales, but inhomogeneity over small scale.
Okay. Like
So the
my
small scale
issue.
inhomogeneities that we see are basically reflecting this 1 in 10 to the 5 fluctuation at the time of CMB.
Yeah, I was thinking that in like if the universe not so uniform, rather homogeneous at that time, in the like typically one would expect thermal equilibrium will also make structure vanish. Like,
Yes.
but then again, I thought that since these are average statements, like it's not like, at least in the present day universe, the universe isn't really homogeneous. Like it's nowhere near that. But over very large scales, some average quantities will come out to be the same as the, if we consider it to be the homogeneous universe.
Yes.
But thermal equilibrium itself is a local process. Like there are interactions involved which can only like causally connect a point to another point,
Yes.
and therefore there cannot really be like starting off with a inhomogeneous picture, like massively inhomogeneous picture. We cannot to get to today's homogeneous picture. I was thinking just through thermal equilibrium.
Yeah, that's right. But the point is that to show this, you have to go to the CMB, the large scattering surface, right? Because
Yeah.
on the large scattering surface, we see. So the point is that if we discover that the universe is homogeneous over scales that is larger than the horizon scale, then only we can say that the thermal equilibrium is not sufficient, right?
Yeah.
Because thermal equilibrium can make the universe homogeneous over the horizon scale.
Yeah, so I was trying to say that if we didn't have inflation, we might not also have today's homogeneity.
Yes, certainly. Because today's homogeneity is a reflection of the homogeneity of the microwave background.
Yeah,
Yeah. In fact, thermal equilibrium, as we will see, that the universe already fell out of thermal equilibrium by the time the last scattering took place. So after that, thermal equilibrium cannot explain why the universe could be homogeneous. Right?
yeah,
It better be homogeneous at that time, right? I mean, in fact, after the last scattering surface, so the universe has only become more inhomogeneous, and that's because of the gravitational attraction. Right? Because gravity is attractive, the small inhomogeneities we can show grow, right? And that's why universe today is much more inhomogeneous compared to what we see in the microwave background.
Yeah.
But the other way certainly wouldn't have been possible. If the microwave background had been inhomogeneous, right, then the universe today would have been much more inhomogeneous over larger scales, right? Small scale inhomogeneities we explain by gravitational effect, right? But large scale inhomogeneities we cannot explain by gravitational effect. So if there are large scale inhomogeneity, then that means there is a thermal equilibrium above that scale.
Yeah.
Sir, can you please explain what is the co-moving Hubble radius?
Co-moving measurement is always in today's metric,
Yeah.
right? So suppose we calculate the Hubble radius at some point, right? Hubble time, say, or lambda dot inverse, right?
Yeah.
Okay. When you multiply this by A0, that's what gives the co-moving value. You always calculate things in today's metric.
Yes.
Right? Co-moving horizon, for example, right?
Yeah.
Is something that you measure in today's metric.
Hmm.
So that's the definition of co-moving, right? It's not the physical horizon at a given time, right? As you saw that the co-moving horizon and the physical horizon differ by this factor of lambda of t.
Huh.
Is
Actually, in the Dodelson book, they explain the inflation theory. They explain the horizon problem by introducing this co-moving Hubble radius. Whereas you introduce the only the
no,
RH.
the way compared, right? I also converted it to the co-moving size only, right? Because I multiplied by
RH.
0. RH, yeah.
Right?
Right?
But they are saying that the co-moving Hubble radius is the inverse of AH. 1 by AH.
Yeah,
H
okay.
is the
H is not the okay. Yeah, you can call it a Hubble radius, but that's not the horizon.
Yeah.
Okay.
No, that's not the horizon.
Exactly. So this horizon problem, right, is not necessarily to do with the Hubble radius. If we believe in Big Bang without inflation, right, then the horizon and the Hubble radius are of the same order. Okay, because that's what we had seen, right? The horizon is roughly controlled by H inverse.
Yes.
But that's not the case, right? Because actual horizon can be different from H inverse, and that's what you saw, right? That so the inflation solves this problem by adding to the horizon.
Yes.
But not the Hubble radius.
Okay, sir.
So the horizon problem should really refer to the horizon, right? Not the Hubble radius. But naively, if you ignore inflation, then horizon is of the same order as the Hubble radius.
Okay.
Any other question? Okay, so let me then begin. Okay, so I'll begin by first writing down the ideal gas results that we had already derived. Okay, but so we wrote down the expression for 1 over V log Q. And this was given by, I'll now write down the result for bosons and fermions together. G over 8 pi square, 8 pi cube, integral 4 pi k square tk, is 0 to infinity. So this is also P by T, as you saw. And this plus or minus, one refers to the bosons, the other one refers to fermions. So this is the top sign refers to boson. Okay, so for boson, this is minus and this is minus. And the bottom sign refers to the fermion. So I'll leave it as an exercise to check that from this one you calculate n, which is 1 over beta del mu of 1 over v log q. So this is given by g over 2 pi squared. So now what I have done is that I have combined this 8 pi q with 4 pi to write it as 1 over 2 pi squared integral 0 to infinity k squared dk. And then here you have e to the minus beta and rho. You will probably recognize that this is the statistics factor at Bose-Einstein formula. Sorry, I should have put a minus plus here. The Bose-Einstein formula statistics factor. I mean, probably you can also look at it as a 1 over e to the beta times square root of k square plus m square minus mu minus 1 or minus a plus 1. Okay. And rho, which is given by mu n minus del beta of 1 over v log q. Okay, you can just calculate from here. Okay. But one can also write down just from guesswork, because basically this is the number of particles in this momentum range. So you just have to multiply by the energy to get the number of to the energy density part in this momentum range. So this is k square dk, and then square root of k square plus m square, and then the same factor. Okay. So these are general formulas. So later we'll consider two limits. We'll study. First is the non-relativistic limit. So this corresponds to t much smaller than m. And then the opposite limit, relativistic limit, which corresponds to t to be much larger than m. Okay, this is not because t roughly is the measures the kinetic energy. Okay? So this is when the kinetic energy is much smaller than m. That's when the particles are almost at rest. Okay? Whereas this is here when the kinetic energy is much larger than the rest mass. Okay, so the mass can be ignored. So particles can be thought of as just massless particles. Okay? So these limits we'll study later. So now let's go back to cosmology and review the equations that we had derived. So what we had said is that if there are L conserved charges, then we introduce L chemical potentials for one for each conserved charge. We introduce L chemical potential which we call mu tilde L. So the variables that are relevant for the cosmological evolution are lambda, rho, well, maybe let me call this T, temperature, and mu tilde L. Okay. And let's look at the equations. So first you have the Friedman equation, lambda tot over lambda square plus k over a0 square lambda square is 8 pi g over 3 times rho. So this I can also write as 8 pi g over 3 sigma I equal to 1 to k rho I, where k is essentially the number of species. Okay. And then you have the energy conservation ddt of rho lambda cube plus 3 p lambda square lambda dot equal to 0. Okay, I had written down earlier in terms of a, but I just divided by a naught to make it in terms of lambda. And I also have d dt of n tilde L a cube equal to 0 for L equal to 1 to L. Okay. So this gives you L plus 2 equations. Okay. And the idea is that we'll use these L plus 2 equations to solve for these L plus 2 variables. Okay. But to do that, you have to first express these rows, all of these variables, okay, in terms of t and mu tilde. Okay. And the way we do it is the following. Okay. So let me remind you. Okay. So we need to express rho p and so rho and p in terms of okay, because only then we have rho p and n tilde, sorry. Okay, we have to express rho p and L tilde L in terms of mu tilde L and t, and then substitute in this equation so that you get these L plus 2 equations in terms of the same variables, lambda t and mu tilde L. Okay, so let me just briefly remind you how that is done. So the idea is that we know ni, pi, and rho I in terms of mu I and t using the expressions for log q. Okay, in fact, using these expressions that we gave on the first slide, right? So using these, we can calculate n, rho, and p in terms of the beta, which is t, and mu. Okay, so mu I for each variable. Okay, so then we use rho as sum over I rho I, p as sum over I equal to 1 to k pi. So these are still expressed in terms of the mu i's and t. Okay. Then you use the fact that mu I is sum over L CLI, sorry, CLI mu tilde L. Remember this is the formula you had derived last time. Okay, so mu i's are expressed in terms of mu tilde L. Okay, so these mu i's you can write in terms of mu tilde L. So that gives you rho and p in terms of mu tilde L and t. Okay. And then also n tilde L is given by sum over I CLI NI. Okay. And since ni's are given in terms of mu I and t, okay, mu i's are given in terms of mu tilde l, okay, we also get n tilde l in terms of mu tilde l and t. Okay. And after you do all that, you substitute in these equations to get a set of differential equations, okay, that gives a lambda t and the derivatives of lambda t and mu l dot in terms of the same variables. Is this clear? Are there questions? Okay, so today we are going to study the consequences of these equations. Okay, some of the consequences of these equations. Okay. So one consequence that I already mentioned last time, but let me now do it specifically. So one consequence, a consequence of these equations is entropy conservation. Okay, which basically says that it's d dt of SA cube, or S, let me, since I'm using lambda, S lambda cube equal to 0. Okay, so let me give a proof of this. Okay. So S, of course, is sum over ISI. Okay. So d dt of S lambda cube, okay, I can write in the following way. So sum over I equal to 1 to k. This is I equal to 1 to k number of kinds of particles. Okay. So here I write this as dSi dt times lambda cube plus 3SI lambda square lambda dot. Okay. And now I'm going to use the following formula. So first of all, dSi dt, the way I'm going to analyze dSi dt is by thinking of SI as a function of rho I and Ni. Right? As I had emphasized that any two of the variables intensive variables can be considered independent. So let's think of SI as a function of rho I and Ni. Okay. So this can then be written as del SI del rho I times d rho I dt plus del SI del Ni d Ni dt. Okay. And it follows that this is given by so del SI del rho I is 1 over Ti, but Ti, all the Ti's are the same in thermal equilibrium. So 1 over T times d rho I dt minus mu I over T. Okay. That's del SI del Ni is mu I over T minus mu I over T times d Ni dt. On the other hand, this one, SI, I'll just write as 1 over T times Pi plus rho I minus mu I Ni. Okay, and now we substitute. So this gives d dt of S lambda cube so let's look at this dSi dt. I substitute some of these two. Okay. So d rho I dt after I sum over I, okay, this just becomes d rho dt. Okay. So first term I write as 1 over T d rho dt times lambda cube. Then this one I keep as it is, so minus 1 over T or minus, let's say, lambda cube over T sum over I mu I d Ni dt. Then we have this term. Okay. So 1 over T, okay, so 3 over T. Okay. Sum over Pi is P. Okay. So P, and sum over y is rho. So P plus rho. And then we have minus 3 lambda square lambda dot sum over I equal to 1 to k mu I n I. Is this clear so far? So now let's combine these terms. Okay, this term over here.
Sir,
Yes, go ahead, please.
sir, why did you omit that I part in rho and p?
Oh, because I wrote it as sum, because it's sum over I, right?
Yeah.
So I'm using the fact that sum over I, rho I is rho, total rho.
Okay.
Rho is, okay, let me write it here. So S is, so similarly here, I should write rho as sum over I equal to 1 to k rho I, and P as sum over I equal to 1 to k pi. Okay, that's why I wrote it as total rho. And similarly here. Is this okay?
Yeah.
Okay. I think here I forgot something. I wrote 3 over t, p plus rho, but lambda square lambda dot I had forgotten. So let me try to do this. Okay. So now let me combine these. Okay. So when you combine this, it's easy to see that we get 1 over t. First, you see d rho dt times lambda cube and lambda 3 lambda square lambda dot times rho. These combine into d dt of rho lambda cube. And then we have plus 3 over t lambda square lambda dot p. But this is 0 by energy conservation. Right? That was one of the equations. Let me go back. Right? That was this equation. Right? So this energy conservation tells us that this is 0. So what we are left is the sum of these two terms, sum of this term and this term. And that's what we are going to analyze in the next slide. So is this okay? Any question here? Okay. So then we get d dt. Okay, let's see what we had. So we had this term minus lambda cube over t mu I dni dt and minus 3 by t lambda square lambda dot sum I equal to 1 to k, and then you have mu I ni. Okay. Now we are going to use the fact. Now use mu I as sum over L equal to 1 to L C L I mu tilde L. Okay, and now we're going to substitute in this. Okay. So we get d dt of S lambda cube as minus lambda cube over t sum I equal to 1 to k sum L equal to 1 to L. Maybe I just write it this way. Let's take this 1 over t common. 1 over t is common in both. So inside I'll write this as lambda cube C Li mu tilde L dni dt plus 3 lambda square lambda dot CLI mu tilde L ni. Okay. But now we are going to use another relation, which is that n tilde L, the conserved charges, is sum over I equal to 1 to k CLI ni. Okay. So now you see the CLI ni, this becomes n tilde L, and similarly CLI. See, these are of course constants. Okay, so you can take it to be inside the time derivative. So CLI ni becomes dn n tilde L dt. Okay. So then this becomes minus 1 over t sum over I, I do the sum over I already. Sum over L equal to 1 to k lambda cube mu tilde L d n tilde L dt plus 3 lambda square lambda dot mu tilde L n tilde L. Okay. So this I can write as minus 1 over t sum over L equal to 1 to k mu tilde. Yes, go ahead, please.
The L sum is from 1 to L, like throughout.
Sorry, yes, thank you. L sum is from 1 to L. I think earlier it was okay. It's clear. You can combine these two now, right? As ddt of lambda cube n tilde L, and this is of course 0. Okay, because ddt of lambda cube n tilde is 0. This is one of the equations. Okay, so we see that this is indeed 0. Okay, so this is what proves the ddt of s lambda cube equal to 0. Okay, now I should emphasize that this is of course not an independent equation. Okay, but often this equation can be easier to use, okay, compared to the energy conservation equation. Okay, so we'll use this equation, okay, and this as independent equation. So in equilibrium, okay, we can, instead of using the energy conservation equation, which involves rho and p, we can simply use ddt of s lambda cube equal to 0. But you should keep in mind that this is not an independent equation. Okay, it comes from the energy conservation and the charge conservation. Okay, are there questions?
So when we say that we have these conservation equations, do we have we also included those charges like electric charges which couple two fields?
Yes, we have also included electric charges. Yes.
I'm asking because I mean these are what we derived using these statistical mechanics. I mean not the we wrote the charges thinking about that they arise from some kind of equations like the two particles going to some other particles.
Yes.
But there might be many of them.
Yeah, I mean, you can think of it, if in the high energy, the theory is described by some quantum field theory, then for every conserved current in the quantum field theory, we'll have such a charge, right? Because this equation, the ddt of lambda cube n tilde L, this one came from d mu j mu equal to 0, right? This arose from the d mu j mu L equal to 0, right? And as I said, so j mu L, okay, so in the co-moving coordinates, okay, we can, so that using isotropy, okay, that J0L is what we are calling n tilde L, this is the density, and GL K, the spatial component, is 0. Okay, for K along R theta or phi.
Yeah, and I understand this. I mean, I'm saying, let's say we were thinking about this an electron and a positron going to two photons.
Yes.
This is an equation, and we can write some conservation equation using this equation. But
Yes.
there's a separate equation of charge conservation above all these kinds of equations. I mean, we can write millions of equations of this type. Two particles.
But the point is, see, when you declare some conserved charge, right? It's not enough that it's associated with one particular process, because all the processes are happening, right? And we'll call something a conserved charge if it's conserved in every process, every possible process.
Yeah.
So that's what is induced from quantum field theory, right? Given a quantum field theory, if it has a certain set of conserved charges, and those are the ones which are going to use in this analysis. So electric charge is one of those, because electric charge is conserved, right? If there are some global symmetries, then those are also conserved. For example, in the standard model, at least to some at some level, the baryon number is conserved. So you use that as a conserved current and so on. But when you say that something is conserved, it's not that you take one particular process and see what charges are conserved. You have to see which charges are conserved for every possible process that can happen. Perhaps I am misunderstanding.
Yeah, I understand, but I think there could be more charges which are conserved above these equations. The global the charges that we get using global symmetries.
Yeah, so those are also included, certainly.
Okay.
See, the charges that you get from global symmetries are included, and the charges that you get from gauge symmetries, because for gauge symmetry, you can also consider a rigid gauge symmetry, right? A global part of the gauge transformation, where the gauge transformation parameter doesn't depend on the space-time coordinates. Okay. And associated with that, there is a conserved quantity. So even in electromagnetism, right? I mean, if you take quantum electrodynamics, JMU is still conserved. And that's why you are including it in our list of conserved charges.
Okay.
But these are the only ones. I mean, if you take a generic process, right? And so you take the collection of all possible processes and you see what are the conserved charges you can construct. And you will find that you get only those conserved charges that you get from the underlying quantum field theory. Okay? If you find that there is some charge that is conserved in all possible processes, and you have not found it in quantum field theory, that means you have missed some symmetries, right?
But that could also happen because we do not have enough energy to that those processes happen.
True. Yeah. So if that is the case, right, then you consider that the number of possible conserved charges, right, can change as a function of energy. That depends on so in standard model itself, right, one can show that at low energy baryon number is conserved, but at high energy it is not conserved, because baryon number actually is an anomalous symmetry. Okay. But the violation of the symmetry, okay, is extremely tiny at low energy, okay, which basically means that the expansion, as this we'll again discuss in detail later, okay, that the relevant physics, right, I mean, to see whether some process is possible or not, you have to compare the expansion rate with the reaction rate, right? And if the reaction rate falls below the expansion rate, then you can say that some charge is approximately conserved, and that then should be included when the reaction rate is much smaller than the expansion rate.
Okay, yeah.
So that can certainly happen. So for example, the E plus E minus going to a pair of photons, right? That tells us that the number of E plus and E minus are not separately conserved. But if the temperature is so low, or the densities are so low, that the E plus E minus annihilation rate becomes too weak, then we will say that the number of E plus and number of E minus are separately conserved. But typically in such situations, the system is out of thermal equilibrium. So what we are assuming here is that the system is in thermal equilibrium. So the rate is not important.
They need not be out of thermal equilibrium. I mean, a photon and a positron and electron can still collide, so they can exchange energy in that way.
Yeah, except that in cosmology, right? I mean, you have to make sure that they can collide within the Hubble time. Right? The average number of collisions of a positron, suppose you have a electron-positron gas, right? The average number of collisions that it suffers in one Hubble time, if that is much smaller than 1, then it's as good as saying that they are not colliding, that they are out of thermal equilibrium. Right? By the time they reach thermal equilibrium, the universe itself would have changed. Because in thermal equilibrium, you specify the density at a given temperature, right? But if by the time you have reached thermal equilibrium, the density has changed by a large amount, then it doesn't make sense to apply statistical mechanics in those situations.
Yeah, I understand that. I was saying, in order to say that electrons and positrons are in thermal equilibrium, we don't need processes like electron and positron going to two photons. They can collide and they can exchange energy. They don't have to undergo this reaction. They don't have to annihilate themselves to photons.
Yeah, but
So,
okay, typically if they collide, right, then the probability of annihilation into photons is the same as the probability of scattering.
okay.
So because see, the long range scattering doesn't really matter. So what we will see is that the electron positron will collide, right? And when they fall out of thermal equilibrium is when they stop producing photons, basically.
Okay. Yeah.
So what we are assuming here, right, is that the system is in thermal equilibrium, thermal and chemical equilibrium. I should have said that it's, when I say thermal equilibrium, I mean thermal and chemical equilibrium. Okay. And only in that case, okay, the number of conserved charges are the exact conserved charges, right? We are assuming that all the processes are possible. We'll see later how to dilute the cases when this is not the case.
Okay.
So here, as long as you are assuming thermal and chemical equilibrium, that means reaction rates are fast enough. Okay, then the only conserved charges that you have are the ones that you get from the quantum field theory. Okay, like the conserved electric charge, conserved global charges, and so on.
So
Yes, go ahead, please.
are all these charges something that we can associate to particles?
Charges are carried by particles, at least because you are using ideal gas, right? So certainly charges are carried by particles.
No, carried in the sense what?
Like electron has positive, negative charge. Muon also has negative charge, right?
No, I'm not talking about electric charge.
Any charge. Baryon
so,
number, lepton number, right?
Yeah.
So it's not that every particle carries its own charge, right? I mean, a charge means it's some quantity that can be carried by multiple particles.
Yeah.
Right? That's what these numbers CIRs, right? These numbers that we saw, these numbers tell us that information. Right?
Yeah. No, I was thinking that can we have some abstract conserved charge, not like governed by some particle process? Like these charges where we can say that baryon number minus lepton number is conserved.
Yes.
That can be seen through interactions, like the quantum field theory interactions.
Yes, but in eventually that is expressed in terms of the fields, right?
Yeah, but that is not abstract. Like we have a definite reaction for it. I mean, okay, we have like worked it out, but I'm saying, do we have, are all these charges in some sense some correspondence with the particles?
See, okay, let me put it this way: that take a single particle state, okay? You can apply, if it's a conserved charge, you can apply the charge operator on the single particle state and you find its eigenvalue.
Yeah.
Those are these numbers.
Yeah, but we can have fields which do not have particle states, right?
Well, here you are assuming that we have taken this ideal gas, right? So you are thinking of strongly interacting system where the particle interpretation is not there. Then of course the NIs don't make sense, right?
Yeah.
Yeah, in that case, yeah, you cannot write in terms of NIs, right? What you have described here. But here you are assuming that you have almost free particles, right? And if you have almost free particles, then the charges are carried by the particles.
Okay. Also, I wanted to know what is our goal in doing all this? Like, what do we want to, like, we want to describe the early universe, but in what terms? Because we have only equations for charges and not content of the charges. Like, we don't know whether that charge is being mostly carried by electrons or something else.
Why not? I mean, electric charge, for example, you know, electron carries electric charge, muon carries electric charge.
Yeah, but like from these equations, we can only comment upon how the total charge behaves, not whether that, I mean, at least so far, I don't see why it would show that that charge is being carried by electrons and not muons.
These equations. Once you
Yeah,
have got the mu's,
equations.
these are these equations, right? See,
Yeah.
we said that we are going to evaluate, we are going to determine how the mu tilde Ls evolve, right?
Yeah.
Okay. Once you know how the mu tilde Ls evolve, we know how mu evolves, right? For every particle, because mu is given in terms of linear combination of the mu tilde Ls.
Oh, there is a one-to-one.
Yeah, because once you determine the mu tilde Ls, look at this. You have these these L plus 2 variables, right? We'll determine lambda t and mu tilde L, okay, how they evolve as a function of time by going through these equations. Okay. Once you have determined lambda t and mu tilde L, how they evolve as a function of time, okay, then you also know how the mu i's evolve as a function of time, because mu i's are given in terms of the mu tilde Ls. Okay. So then we can substitute in these equations to find the number density of each kind of particle. Yeah, that's where this helps, right? The statistical mechanics helps in that way, that once you have determined how the independent variables evolve, we know exactly how the number densities and the energy densities carried by each species of particles evolve.
I mean, okay. Suppose in one Hubble time, there are like two possible reactions, but one of them is much more likely or much faster. Like
That
something
doesn't,
like,
that doesn't matter as long as both
but
reactions are faster than the Hubble time.
yeah, if like this analysis would show that it doesn't matter, but it should matter.
No, it doesn't matter. See, this analysis tells us that as long as the system is in equilibrium, this is the result. Because if some reaction takes place faster, very fast, right? The opposite reaction also takes place very fast.
Why? Like,
That's the detailed balance, right? In thermal equilibrium, right, the reactions always match up, right? If some reaction takes place very, very fast, right? Then, I mean, it's like QED Feynman diagram and a quantum field theory, right? You can turn the incoming states into outgoing states. It remains the same Feynman diagram.
yeah.
Right? So the having fast reaction rate doesn't matter. Okay, the opposite reaction also takes place. That's the thermal equilibrium is reached. Right? And this equation is clearly telling us that the actual reaction rate doesn't matter as long as you have reached thermal equilibrium. However, sometimes you don't reach thermal equilibrium, and there it will matter, right? And you have to take into account those cases. See, as long as you assume thermal equilibrium, these equations that you have written down so far are enough to tell you precisely how the various densities evolve, various densities, pressures, and energy densities of individual particle species, how they evolve as a function of time.
Yeah, but I mean, a lot of things have changed because of this assumption. Because, like, are we even able to justify this assumption?
Thermal equilibrium.
Yeah.
Yeah, we can justify it as long as the reaction rate is larger than a Hubble rate, right? And we will see how to calculate that. So as I said that, I mean, this is true when the system is in thermal equilibrium, right? But it is not true that every reaction is in thermal equilibrium. And you have to take that into account. Right now, we are saying that what happens if the system is in thermal equilibrium, if all the reactions are possible.
Yeah, okay.
Is this clear? Are there other questions on this? So it should be at least clear that the equations that you have written down, okay, which you have written down assuming thermal equilibrium, okay, but as long as those equations are valid, okay, we can use those equations to determine the actual number density and pressure and energy density associated with each particle species, okay, using this formula. Okay, any other question? Okay, so let me then go ahead. Okay. So you are going to now give some other further results. Some further useful results. Okay, so one we saw is the entropy conservation. Okay, so these all follow from the equations that you already have. Okay. So the first one is that the particle and antiparticle. Always carry opposite values of the conserved charge. Okay, which basically means that when you calculate n tilde L, let me write it. So n tilde L, remember he wrote it as sum over L, sorry, sum over I equal to 1 to K C L I N I. Okay, but I can also write this as sum over alpha equal to 1 to K by 2. Now I am comparing the particles and antiparticles together. Okay. CL alpha times N alpha minus N bar alpha. Okay, so this corresponds to particle, and N bar alpha is the density of antiparticles. Okay, and what this is saying is that in the expression for a conserved charge, okay, the particles and antiparticles contribute oppositely, which means if the particle carries the value CL alpha of the conserved Lth conserved charge, then the antiparticle will carry the Lth conserved charge as minus CL alpha. And this you are familiar with from quantum field theory, right? The electrons and positrons carry opposite electric charge. In fact, they carry opposite of every charge, if there are such charges. And roughly it has to do with the fact that the antiparticle is like a hole, right? It's the absence of a particle in the Fermi sea. So it's natural that the antiparticles will have the opposite carry the opposite values of the conserved charge compared to the particle. Is this point clear? Okay. This can also be written in the following way, that this can also be thought of as saying that CL alpha bar, this is the CL for the antiparticle, is minus CL alpha. Okay. And this also, this can be translated into mu. Okay, so if you take mu alpha, then the definition is this is L equal to 1 to L C alpha L mu tilde L. Okay. And the mu for the antiparticle, mu bar alpha, is sum over L equal to 1 to L. It should be CL alpha bar mu tilde L. Okay. But that's minus sum of L equal to 1 to L CL alpha mu tilde L. Okay. So this tells us that mu bar alpha is minus mu alpha. Okay, so that means chemical potentials are opposite. Is this clear? Okay. So this also has a corollary. And that's that if a particle is its own antiparticle, is its own antiparticle, then mu alpha is equal to 0. Okay, because then mu alpha is minus mu alpha, and that means mu alpha equal to 0. Okay. And this, of course, we are familiar with, the e.g. photons, which are its own antiparticle, they have mu equal to 0. Okay. And that's because the photon number can be changed without violating any concept charges. That's all that it means. Okay, so this is the first observation. Now the second observation. Okay. So here we first begin with okay, this is an observation in statistical mechanics. This doesn't have to do with cosmology. Okay, in fact, the previous one was also an observation in statistical mechanics, right? Assuming formal equilibrium, this is a result. We never talked about time evolution or anything anywhere, right? This is all this can be said at a fixed time. Okay, the second observation is also of that kind. Okay. So first, let me remind you that what this is saying, that if for a given system we know the n tilde else, then we can find mu tilde else. Okay, so this is the data, and this gives the mu tilde else. Okay, and the procedure, let me write down the procedure. Okay, or the algorithm. Okay. So the first step is to write n tilde L equal to sum over I equal to 1 to k C L I N I. Okay. Now then we use the fact that this Ni, this is given in terms of mu I and t. Okay, and that again, let me remind you, that's from here, right? N is given, each Ni is given in terms of mu I and t. Okay. Then we use the fact, so this is a known function, so each Ni is a known function of mu I and t. Okay. Then use mu I equal to sum over L C L I mu tilde L. Okay. And this gives n tilde L in terms of mu tilde L for fixed t. Okay. So this means what? This means that we have L equations in L unknowns. right? Because n tilde L's are given. Okay? That can be used to determine mu tilde L. So you have L equations in L unknowns. Okay? And typically, at least except in pathological cases, this solution is unique. Okay, because you have these are algebraic equations, L equations in L unknowns. Okay, so typically you have a unique solution. Okay, are there questions? Okay. Now suppose that for some system n tilde L is 0. Then we claim that a solution for mu tilde L's is mu tilde L equal to 0. Okay. So what we will show is that this solves the equation. Okay. And then if the solution is unique, which as I said is true under some general conditions, okay, then this will be the only solution. Okay, but we'll try to verify that mu tilde L equal to 0, okay, solves n tilde L equal to 0. So is this statement clear? Okay, I should have said that it's this is both statements are true, that what is given is that for some system n tilde L equal to 0 for every L. For all L. And this is for also for all L. So this gives you L equations because we are setting n tilde L equal to 0 for each L. So L runs from 1 to capital L. And the solution is mu tilde L equal to 0 for each L. Okay. So let me briefly give the proof. Okay. So if mu tilde L equal to 0, then mu alpha, it is sum over L, Ci alpha, sorry, Cl alpha mu tilde L, this is 0. And similarly, mu bar alpha is also 0, which is minus mu alpha. It is also 0. Okay. So now let's look at the expression for n alpha. So n alpha was g over 2 pi square. Okay, remember the first equation, equation that we wrote down on the first page. Z dk k square, okay, and e to the power minus beta square root of k square plus m square. Okay. No minus mu because mu's are all 0. Okay. And here you have 1 minus or plus e to the power minus beta square root of k square plus m square. This is m alpha square. Okay. N bar alpha has exactly the same expression because it would have differed from n alpha in having mu alpha and mu tilde mu bar alpha opposite signs. So one, if this was minus mu alpha, this would have been plus mu alpha for the n bar alpha. Okay, but mu is 0, mu alpha is 0 for the solution. So this is the same as n alpha. Okay. And this means that n tilde L, which is sum over alpha, now I'm writing in terms of alpha, CL alpha, n alpha minus n bar alpha is 0. Okay, it is 0 for every L, okay, because n alpha and n alpha bar are the same. Okay. So you see that this solves the equation. Equations are solved. Is this point clear? So let me state it again. Okay. So what we are saying is that if you have a system for which all the conserved charges are 0, okay, then there is a solution, okay, and usually it's a unique solution, okay, for which all the mu tilde L's are 0. Okay. And one of the particular property of that solution, okay, is that the number of particles and antiparticles is the same. Now, clearly, if the number of particles and antiparticles are the same, then the L tilde L's are 0 because particles and antiparticles carry oppositely to conserved charges. Okay. But what this is showing is that it's also the reverse is also true. Okay. That if the conserved charges are all 0, then the number of particles and antiparticles are the same in thermal equilibrium. Is this point clear? Okay. Now, this looks like a peculiar result, or maybe valid in only special cases. Okay. But this, in fact, is a very important result in cosmology. Okay, so let me explain this. So the importance of this result in cosmology. Is that this is a very good approximation for most studies. Now, you may wonder that how can it be very good approximation, because you know that our universe has more matter than antimatter. Okay. So there is some excess baryon, for example. Okay. So how is it possible that this is a good approximation? Okay, because it certainly doesn't seem to be valid in our universe. Okay. However, the reason that it's still a good approximation is because we can calculate the number of photons divided by number of baryons. Okay. So let's count the number of baryons as everything as baryons. Okay, actual number of baryons is of course even less. Okay, but let's imagine that the all matter density was protons. Okay. So then this we have seen is about 1 proton per meter cube. Okay. Number of photons is typically 10 to the 8 to 10 to the minus 9 times larger. Okay, the conservative value is 10 to the 8 per meter cube. Okay. So it's a number of photons overcomes, exceeds the number of baryons by a huge amount. Okay. So which means that for the statistical mechanics, the effect of this small tiny excess of baryons on the photons is tiny. Okay. So you can simply ignore the presence of baryons for most statistical analysis, the presence of the excess baryons. Now, of course, this is true only in general statistical processes, but clearly this cannot be true. Clearly, this approximation is not useful when we are studying processes that involve these excess baryons. Okay. So, for example, in the later we'll calculate the ratio of the helium to hydrogen. Okay. And here, of course, helium and hydrogen are all formed by these excess baryons. Okay. So for calculating this ratio, you cannot ignore the excess baryons, right? Because it's the excess baryons which form hydrogen and helium. Okay. So for such processes, we have to take into account the excess baryons. But for most other purposes, most statistical analysis, we can simply ignore the number of excess baryons and work with the approximation that all the conserved charges vanish, and hence we can set all the mu's to 0. So from now on, okay, in much of the analysis, we will simply set all the mu's to 0 and proceed. Okay, because as you will see that simplifies life considerably.
So can you explain it? Why did we compare the number of baryons to the number of photons?
Okay, because what we'll see later is that this ratio remains the same. This doesn't change very much as a function of time. Okay, at most changes by order 1. So in the early universe, also this was the ratio that was involved. Okay, and it's the number of particles, right, that is useful for statistical analysis, because the entropy, right, goes as exponential of the number of particles. Okay. So for a given statistical system, the contribution of the baryons to entropy is tiny compared to the contribution of the photons. Okay. Now you can say baryons contribute to energy, right? But the part of energy that it contributes, right? I mean, the reason that today's universe is matter dominated, right? The matter dominates the radiation is because of the rest mass, right? Because of the rest mass of the proton. But rest mass really doesn't play any role in statistical mechanics, right? You can just subtract it off. It's the kinetic energy that plays a role. So because the number of baryons is so small compared to the number of photons, as far as the statistical mechanics of the system is concerned, we can simply ignore this number of excess baryons. Is that point clear?
Yeah, okay.
Not so clear?
Yeah, I mean, I was thinking, I mean, could you go to the last page?
Last page, yes. Here. Or earlier?
Yeah, this one. You claim that, okay, this was, if NL is 0, then all the mu are 0.
Yes.
Is it not the other way?
Yeah, it's also the other way, right? So what we are saying is that there are L equations with in L unknowns, right? This n tilde L equal to 0 is L equations, right? And mu tilde L's are the unknowns that you have to solve, right? And the procedure for solving it is what I indicated in the previous slide, that you have to express the n tilde L's in terms of these. Ni's are given as a function of mu i's and t, and mu i's in turn are given in terms of mu tilde L's. So using this, we can express the n tilde L's directly as a function of mu tilde L and t.
Okay, yeah, I understood. I was thinking of photon having a conserved charge, but that is 0. Okay.
Yeah, photon doesn't have a conserved charge. Yeah, exactly.
Okay,
yeah. So there are no conserved charges associated with. So n tilde L equal to 0, right? So that basically means that the n tilde L, okay, is okay. N tilde L equal to 0. Suppose it's not 0, but small, right? Now you can ask what do you mean by small, right? So we'll say it's small provided it's small compared to typical n alpha. In a given statistical system, when the n tilde L is small compared to typical n alpha, then we can say that this approximation is good, right? We can just set the mu's to 0. And these n alphas are like the number of photons in CMB, because in the early universe also this ratio, as I said, will remain the same. So n alphas, the order of magnitude of the n alphas is played by the number of photons in the CMB, and the order of magnitude of the n tilde L's is played by the number of excess protons in the in today's universe. Right? So that's why that ratio is important, is a relevant one. Because that tells us what was the ratio of n tilde L over n alpha in the early universe also.
Yeah.
Is this-
Okay. Yeah.
Any other question? Okay. So let me now discuss the two limits. So the first is non-relativistic. We are studying the non-relativistic limit of the relations, of the various relations that we wrote down on the first slide. Okay. So let's start with P over T. Okay, this is 1 over V log Q. So this was minus plus G over 2 pi square integral dk k square. Okay. So this is small because since, okay, I should have written the limit. Okay. So this is T is much larger than, sorry, T is much less than M, which means beta is much larger than 1 over M. Okay. So beta M is a large number, so e to the minus beta M is small number. Okay, so you can just expand this logarithmic. Log of 1 minus plus x is minus plus x. So I can write this as g over 2 pi square integral 0 to infinity dk k square e to the power minus beta square root of k square plus m square. Okay, and now because beta is very large, right, we can see that k will be restricted to small values, so we can further expand this in powers of k. Okay, because m is large, okay, well, beta m is large. Okay, so you can further expand this in powers of k. So this I can write as g over 2 pi square integral 0 to infinity dk k square e to the power minus beta m minus beta k square by 2m. Okay. So this basically is the usual classical statistical mechanics that we study when k is much smaller than m. Okay. And this is a Gaussian integral. You can easily do this. Okay. And I'll leave this as an exercise. We just do the Gaussian integral to show that this is g over 4 pi square e to the minus beta m times square root of 2 pi m over beta q. I think 2 pi m over beta q, yes. Okay, and what we see is that this is small due to this e to the minus beta m, which is e to the power minus m by t factor. Okay, in fact, it's exponentially small. Okay, so the pressure over temperature is falling off exponentially, is becoming exponentially small. Okay, when t becomes much smaller than m.
Sir, it is 2 pi m by beta whole to the power 3 by 2 or?
Yeah, beta cube. I didn't say this is beta 3. I think I made a mistake here. Beta cube. Yeah, because this is dkk square, so you can easily do the scaling.
Yeah.
This is correct, right?
Yeah.
No, whole cube.
Whole cube, yeah. Whole
By m by beta whole to the power 3 by 2.
whole to the power 3.
Yeah. So the square root is over the whole thing.
No, cube is also over the whole thing.
Cube is also over the whole thing. Are you
We
sure?
have a decay k square, so
Yeah. Okay. Thank you.
it's not just a Gaussian.
Right.
It's a
Yeah. Okay. So you are saying that this is
yeah.
because you can just scale k out right from this, and that will give a 2m over beta. Yeah, this is correct. Thank you. Okay. Any other question? Okay. So you can calculate also n. So n was given by, let me remind you, g over 2 pi square integral dk k square e to the power minus beta square root of k square plus m square. Now I'm setting mu equal to 0. 1 minus e to the minus beta square root of k square plus m square. Okay. Now this term is small. This term is small, so I can just set it equal to 0. Okay. And it gets back to the previous expression, right? The p over t expression. So this is also gm over 4 pi square e to the minus beta m times 2 pi m over beta to the power 3 by 2. Is this clear? I have a feeling that this 2 pi is probably not raised to third power, no?
It is because we had actually the integral you have written has a 4 pi also, so in the numerator.
No, that doesn't have. Because I cancel that 4 pi against the 8 pi cube. You see this?
No, it was 8 pi square. So
No, 8 pi cube. It was g over 8 pi cube times 4 pi. Let's go back to the first slide. Yes, just g over 8 pi cube times 4 pi, right? So there's a 2 pi in the denominator. So I think you're right that the m, no, in fact, I think I wrote it correctly the first time. I go back to the last slide, 1 minute. Okay, let's look at here, right? No, this, I should have written it this way. I think the way I had written it is the following. I'll write it the way I had written it. I copied it wrong. I had written it as square root of 2 pi m over beta cube, okay, and there's an m outside. Okay. So this is really m cube. I mean, when you take this m inside, it's m cube over beta cube, right? Which is, I think, what you have been saying, m over beta to the 3/2. Okay. But square root of 2 pi comes only once, right? Because you will do the Gaussian integral first, then you just take a derivative, right? The derivative doesn't generate extra factor of square root of 2 pi.
yeah.
Okay, so I think this is correct up to maybe at most a numerical factor, but I think this is probably okay. Okay, anyway, you have to check this. Is this okay? Okay, so this is also the same. Let me correct it. So I'll write this as square root of 2 pi m over beta cube. And there's an m here, right? So it's a 2 pi m cube over beta cube. So I think that will satisfy everybody.
No, the factor is, I think it would be 8 pi because we are taking the derivative with respect to beta by 2m, not
Yeah,
by
so
beta
that
by
4
m.
pi square outside should remain 2 pi square.
This should remain 2 pi square.
Yeah.
Okay. I don't know how we got this 4 pi.
It's actually I mean, we are if you go to the integral in the last page,
Yes.
So we here it is dk k square e raised to minus beta k square by 2m. So
Yes.
we have to take the derivative with respect to
Okay.
beta by 2m.
Okay. Yeah.
So
So you are saying that 2m, that 2 will cancel the half that you get from the square.
yeah,
Okay.
yeah,
So this should be 2 pi, you are saying, right?
yeah.
Then everybody will satisfied. If I make this 2. Okay. So this is something you should check. Okay. It's not very important at this stage, but this is something you should check. Because ultimately you have to find a numerical factors also, right? When you actually apply this to physical problems. Okay. So, but whatever factor is here, that same factor will be there in the next slide, right? Because this is the same integral. Because we are setting this equal to 0. So let me write this as 2 pi square. Okay, but I'll check this also. Okay. And rho also you can similarly calculate, but you don't really have to do that because you just multiply this n by m, right? Because they are energy per particle is now m, right? In non-relativistic limit, you can just ignore the kinetic term to the first approximation. So this is a gm square over 2 pi square e to the minus beta m square root of 2 pi m by beta cube. Okay, are there questions? Okay, so what this is showing, okay, I think that's the physically important thing, is that the number densities, right? And in fact, everything number, I mean, you can say because the number density is falling off, the energy density is falling off, and everything else is falling off. Okay. So the number density falls off exponentially. As T falls. Okay, and T of course falls as the universe is expanding. Okay. Now physically, what the reason that it's happening? So physically, what is the process? So in thermal equilibrium, okay. So let's take the alpha particle, right? So alpha bar, okay, particle antiparticle can go into radiation and vice versa. Okay. But as the temperature falls, okay, the average energy density in the radiation is falling off. Okay. So then typical photons, okay, or typical other light particles, okay, do not have enough energy to produce an alpha bar pair, right? Because you need at least 2m. Okay. But of course, it's not entirely impossible because when you're talking about a black body radiation at a temperature T, there are always some tail photons or tail of other particles, okay, which have high energy, right? Because after all, black body radiation is a distribution. Okay. So there are some particles which do have enough energy to produce alpha bar, okay, but number of those particles is small, okay. And that's why in this balance, right, it becomes harder to produce alpha and alpha bar. Where on the other hand, alpha and alpha bar of course can annihilate to radiation. Okay. So the density of alpha and alpha bar that balances this two-way process, okay, falls off exponentially. Okay, because the reverse process is now exponentially suppressed because the radiation, the number of photons of sufficiently high energy is exponentially small. Okay. So that's the physics of why the number density of alpha and alpha bar fall off exponentially. Is this point clear? So the point is from the statistical analysis, of course, we see this explicitly in the formula. Okay. But you can ask, can you understand it physically? And this is the reason why it happens physically, because they are simply the number of photons which have enough energy to produce alpha bar pair is small. Okay. On the other hand, alpha bar are annihilating into photons. Okay. So most of the alpha and alpha bar go into photons. Okay. and only occasionally some alpha and alpha bar are produced, which balances this process. But this cannot continue indefinitely. So at some point, when the density is low enough, okay, and this is something that we'll calculate how to decide on when the density is low enough. Okay. But when the density is low enough, okay, the number of collisions, the number of times a alpha encounters an alpha bar in one Hubble time is much less than 1. Okay. That means that before the alpha encounters an alpha bar to annihilate, okay, the universe has doubled its size. So the density has fallen even further. Okay, so the whole then the statistical equilibrium is lost. Okay. So in this case, we say that the alpha falls out of equilibrium. Okay. They are also called freeze out. Okay. So a particle simply freezes out of the statistical ensemble. So after freeze out, what happens? After freeze out, you can use the approximation that the alpha particle never encounters an alpha bar, it just remains as it is. Okay. So after freeze out, the number of alpha particles goes as n alpha, n at freeze out. Okay, so this is the number of alpha particles at the freeze out, okay, times lambda f. Yeah, lambda f over lambda cube. Okay. Because after freeze out, n alpha times lambda cube is conserved. Is this point clear? Okay. So this is useful, okay, because this can be used to calculate what is called a relic density. Okay. So this can be used to calculate So for example, if dark matter is a collection of heavy particles, then it may be the relic density after freeze out. Okay. So later we'll study this in more detail, but the basic idea is that suppose somebody gives you a theory of dark matter. Somebody says, okay, here I have a Lagrangian, okay, and this Lagrangian has a new particle. This particle is a dark matter particle. Okay. Then what you can do is that you can take that Lagrangian, you can calculate the cross section. Okay, you can see what you can study this process. Okay, so once you have given the Lagrangian, you know the dark matter masses, dark matter properties, and so on. And then you can say, okay, let's see what happens as the universe evolves, right? According to that Lagrangian. At some point, you will find that dark matter, the temperature has fallen below the dark matter mass. The density of dark matter is reducing rapidly. And at some point, the dark matter freezes out. If you know the properties of dark matter, you can calculate at what point the dark matter freezes out, because you have to look at the number of collisions, the alpha encounters an alpha bar, okay, in 1 Hubble time, and you can calculate the freeze out time. Okay. And based on that, okay, you can calculate this number. Okay, you can calculate this number today. Okay, because you can calculate lambda f because you know TF. Okay, the temperature at which the dark matter freezes out, okay, and you can calculate this number. Okay, NF you can calculate, right? Because NF, let me show you again how to calculate this, right? I mean, this should be very clear. Okay. So to calculate NF, you will just substitute in this formula, right? Or you can use the non-relativistic formula, relativistic formula, whatever formula you have. You substitute in this formula, okay? And then knowing the temperature at which it freezes out, you substitute beta equal to the beta freeze out temperature. Okay. Mu you can set equal to 0. Okay. You can calculate what was the number density of dark matter at the time of freeze out. And you, because the temperature is known, you can also calculate what is the value of lambda at the time of freeze out. Okay. Knowing that, okay, you can then find the subsequent evolution of the dark matter density. It will just fall off as 1 over lambda cube. Okay. And you can calculate this today. Is this point clear? Okay. So the other point I want to add is that the freeze out may happen also when the particles are relativistic. Okay. You see here, we said that the freeze out happens because the density falls, right? And then the number of times the alpha encounters alpha bar becomes less than 1. Okay. But that's not the only reason why freeze out may happen, right? I mean, it could be that the interaction strength becomes small enough, okay, at some energy scale, so that the interaction that even though the densities are large, okay, temperature is the particles are relativistic. Okay, even then it may happen that the reaction rate, okay, falls below the expansion rate. Okay, you may find that the 1 Hubble time, the particle simply doesn't interact because its interaction strength is small. Okay. And again, I mean, later, maybe next time, we'll see how exactly to compare this, how exactly to calculate the reaction rate and compare the Hubble expansion rate. Okay. But when that happens, that's the freeze out time. Okay, it may dark matter may still be relativistic. Okay, or whatever matters may still be relativistic. Okay, and if it happens when it's relativistic, then typically the densities are much larger, right? Because this exponential suppression is not there. Okay. We'll form next time we'll derive the relativistic version of this formula. Okay. But irrespective of when the freeze out happens, okay, after the freeze out, this formula holds. Okay, so you can calculate NF, okay, knowing the temperature at which the freeze out happens, and then from there on you can find its subsequent evolution. Is this point clear?
These NF, these NIs are
Yeah.
not just for fundamental particles, right?
Well, you are thinking it of a fundamental particle, but it could also be protons and antiprotons, for example. Okay. At low enough temperature, those are as good as fundamental particles.
Are protons, what is the baryon number for protons?
1. So protons and neutrons carry baryon number 1.
Also, the bound state energy of proton, is it the same as that of an antiproton?
Yes, so the proton and antiproton have exactly the same mass. That's a consequence of CPT theorem. Yeah, the CPT invariance guarantees that the particle and antiparticle always have the same mass.
Yeah, so this dissimilarity between matter and antimatter is also with respect to bound states.
Yes.
Yeah, okay.
Yeah. So the excess of matter over antimatter, right? That basically says that this mu's are not exactly 0. Clearly, right? That the n tilde L is not 0, and hence mu tilde L cannot be exactly 0. Okay. But it's small enough so that for most processes, it's irrelevant.
Yeah, okay.
Okay. Okay, so maybe I'll stop here, but let me just say that we'll use this idea of freeze out. Okay, in fact, we will see that the neutrinos freeze out quite early in the game. Okay, because neutrinos are weakly interacting. Okay, and using that physics that the neutrinos freeze out early. Okay, and we'll calculate precisely when the freeze out happens. Okay, we can actually calculate. Okay, so application of this idea. So application. Neutrinos freeze out when they're relativistic. But I should say that these have not been detected. Okay, this is theoretical prediction, but it better be true. Otherwise, the whole standard model will fall through. Not detected yet. Okay, but they must be there. Okay, and we'll see what they are. In fact, we'll not only be able to determine the density, we'll also determine their spectrum, right? The black body radiation, and we calculate the temperature from this freeze out physics.
So what did you say? If it is detected, then the standard model.
No, if it's not detected yet.
Okay.
But if we can, construct experimental apparatus that are sufficiently sensitive, we better detect it, right? If the experimental apparatus is sufficiently sensitive to detect this, and if they don't find it, then that would mean that the standard model must be wrong. Right? Because it's a prediction of the standard model that neutrinos must be present in today's universe with a very specific density and temperature and so on.
Sir, can you please suggest some book for this statistical analysis of this early universe?
I think Weinberg's book will have it.
Okay.
I mean, it has it in a somewhat, haphazard way, but it certainly has everything that I'm discussing here.
Okay. Thank you, sir.
Okay. Are there other questions?
So this neutrino freeze out would have occurred very long ago?
It happened at a temperature of order, I think about a MeV.
Okay.
So it happened reasonably long ago.
Okay.
So and it was certainly relativistic at that time. Okay. So this freeze out is not because the densities become very small, but because the reaction rate became small. Okay. Any other question? Okay, so next time we'll then first begin by writing down the relativistic limit, okay, because that is the opposite of this, okay, that we haven't discussed, but that will be very important because many of the formulas that we'll be using, that will play a crucial role. Okay. So we'll discuss the relativistic limit like this, okay, that's when beta is very small compared to, or beta is smaller, temperature is large compared to M. Okay. And then we'll study the physics of this freeze out in more detail. Okay, so I think I'll stop here. Any other question? Okay, so I'll stop and we'll meet next week.